Welcome to Unit 7. We're going to begin by filling in some definitions here. We're going to start with the exponential function, and then we're going to talk about the logarithmic function tomorrow and how they're related to one another. The beginning we need to start with is what parts are the exponential function. The first part is the base, and the second part is the exponent. The base is defined as the value that is b. b is located inside here. That is used as a factor. So the example here is 3 to the 4th. So the factor is 3. You're going to multiply it 4 times. The exponent is the value x, again in this problem here. That determines how many times the base is used as a factor, or how many times the base is being multiplied. So you can see that determines how many 3's you are going to write. The next thing we're going to look at is we are going to look at how to graph exponential functions. In each one of these examples, I begin by showing how to get the answers for the f of x values, and then after that I simply just plug them in to the table. 2 to the x power when x equals -3 is saying 2 to the -3rd power. From your properties of exponents, you remember that when you have a negative exponent in the numerator, you simply take its reciprocal or move it to the denominator of the fraction. That's how it turns into 1/8. -2, 1/4, -1, 1/2, so on and so forth all the way through. You get a curve, an exponential curve, that looks like this. Now, because negative numbers don't result in negative values of y, instead fractions, there's no way that this graph is ever going to cross the y-axis. Which means that in this case, because there are no transformations vertically, the asymptote of this exponential function is the horizontal line y equals 0. Now, because the graph will never touch this asymptote, that affects the range value. Notice that the range value in set notation is y is greater than 0, and in interval notation you have parentheses rather than brackets surrounding your 0. The domain is all real numbers because this will always get a little bit bigger. It'll continue to curve. And moving on to number 2. Number 2, same thing. What we're doing here is we're plugging in the values of x into the exponent. When you have a negative exponent, it moves that value to the denominator of fraction. That's why it's 1/27, 1/9, so on and so forth. Because there are no vertical transformations, the domain and range, well, the range especially, because the domain is always all real numbers, the range has no changes. Because of the asymptote, it will not cross, so it cannot be equal to 0. Question number 3 represents a new and different curve. Notice that the value of b, the base, now is turned into a fraction. You'll notice also how that affects our curve. It changes its orientation. So when you have a value of b which is greater than 1, you have what is known as growth. When you have a value of b which is less than 1 but greater than 0, you have something that is called decay. Exponential growth and exponential decay are important for this unit, especially when we get to word problems later on and your applications of exponents and logs. Notice what happens when you have your value, your negative values placed in here. Notice that your negatives switch position and you get the larger numbers first, and then the smaller number, the fraction numbers, that come second. So here is your curve, and here is your domain and range. Again, because there are no vertical transformations, there is no change to your range because of the lack of change on the asymptote. Please take a few minutes now and solve example number 4. Be ready to share that information in class tomorrow. Here's a summary about the similarities and differences between exponential functions when you have the value of the base greater than 1 versus a fractional value between 1 and 0. Continuing on, general form of your exponential parent function looks like this. B is your base and x is your exponent. Remember, the base can change. So the technical parent function is whatever the base is without any of these other transformations attached to it. Remember that A is either stretch or compress, depending on whether it is greater than 1 or a fractional value. Remember also, if there's a negative attached to the A, that you have a reflection, and that reflection will be from up to down. Right and left is your H. As usual, it is opposite of what you think. Up and down is K, and as usual, it is also the same as what you think. We'll go through a couple examples now based on transformations of parent functions. We're going to create a new graph, and then we are going to state the new domain and the new range. What I'm going to do here is every time an asymptote is present, I'm going to draw it using a dotted line. So notice that I have a transformation that moves this to the right 3 units and up 1 unit. That means my asymptote has moved from 0 to 1. That also means that my graph is shifted up 1 unit. So remember, the parent has that critical value at 0, 1. Now it's going to be up to 0, 2 and over 3 units. So that critical value is now here. When I draw my curve, it's going to get close to but not touch the asymptote, and then it's going to curve drastically upward after it passes that critical value. The domain of this function is going to be all real numbers. And now because the horizontal asymptote has moved, that is how I know what my new range is going to be. Set notation, interval notation. Number 6, notice now you have a multiplier out in front. Notice it does not stretch or compress because it is 1, but instead reflects. Notice your B has turned into a fraction. That means now I have decay. So the general curve of my parent is going to look like that, as opposed to growing like in question number 5. All right, so we'll begin with the asymptote. The asymptote has moved down to -2. Because there is no stretch or compress on this, I still have that value of 1 or 0, 1. Okay? But this time it's moved up to -1 from -2. Now because I have a reflection, that means that rather than moving up, I'm going to move down on the graph and put the curve there. Now remember, the general sloping form of a decay would look like this. So that means that my decay, when it's reflected, is going to look like this. Alright, the domain has not changed, all real numbers. The range has drastically changed. We begin at -infinity and we go to -2. Notice how that's switched. Always start with the smallest value first. And if you're in set notation, that's going to be y is less than -2. Alright, in questions number 7 and question number 8, we're going to use the parent 2 to the x power, and we're going to see what happened in this problem. Okay? So what I'm going to really look for here is I'm going to look for that critical value. That critical value is the one that is normally at 0, 1. But in this case, it does not occur until all the way over at 4, 1. Which means that I have a shift to the right 4 units. Because the parent function is 2 to the x power, it's going to be y equals 2 to the x power minus 4. The domain and range of this, even though it didn't ask for it, I'm going to continue to do that just so it makes it familiar for us. All real numbers, and your range is from 0 to infinity. Now in this one, we're looking for that 1. I don't see it. I don't see it at 0, 1. I don't see it anywhere shifted along here. That's the one that gets closest to, but that's not it. So instead what I'm going to look for is I'm going to look for that value of the stretch. And it looks like my value of my stretch is 3. So that means as I write this, it's going to be y equals 3 times 2 to the x power. That is not 6 to the x power because of order of operations. Those must be kept separate from one another. Domain and range of this one is unchanged from the domain and range of question number 7. All right, now we're going to look at it from a different point of view, and what we'll do here is we'll describe the transformations which occur. Take them one at a time. -3, down 3. +1, left 1. 1/2, that's your compression. That's a vertical compression by a factor of 2. Question number 10 and question number 11 brings back some old memories. Way back in Algebra 1 when we were talking about how to determine your values. So what we'll do here is we'll look carefully at the change in x. The change in x is +1 every time. That's a very important thing to understand. If it is not a constant change, we have to do some work to create that constant change before we can actually do what we're going to do here. Okay? So let's remember back to what we were taught previously. If a function is linear, then the first difference is constant. If a function is quadratic, then the second difference is constant. If a function, and this is the new part, is exponential, then there is something called a constant ratio. So let's do some work here on the first difference. From 1 to 0.25, the difference is 0.75. 1 to 4 is 3. 4 to 16 is 12. And 64 to 16 is 48. Constant difference is not, the first difference is not constant, so that means it is not linear. Now I'm going to go from 0.75 to 3, and that's going to be 2.25. From 12 to 3 is 4. Sorry, 9. Let's do some subtraction, shall we? And from 12 to 48 is 36. The second difference is also not constant, so that means that it is not quadratic either. The constant ratio is determined by dividing consecutive y values together. 1 divided by 1/4 is 4. 4 divided by 1 is 4. 16 divided by 4 is 4. And 64 divided by 4, 16 is 4. So the constant ratio is constant in all of them. That means it is exponential. Okay? In question number 11, again, we're doing the exact same thing. Determine that x is in fact counting. The constant difference here is 1, or the first difference. The first difference here is 1. The first difference here is 1, and the first difference here is 1. That makes question number 11 linear. Please make sure you look over your notes and make sure you understand how to transform parent functions. Please also solve problem example number 4 before class begins tomorrow.